So let's say that we use the velocity as our primary degrees of freedom, right? Because this is a self-propelled particle. So what we want to compute first are the fluctuation of the velocity of each individual. That is, the velocity of that particles minus the spatial average of the velocities of all the other particles. So this is the individual deviation from the average direction of the group. And if your degrees of freedom is something else, it doesn't matter. You want to compute the deviation from the average behavior, if you want, of the group, right? So you're not interested in the individual behavior, but in the deviation of the individual behavior from the mean behavior of the group. And then you can compute the correlation function of the fluctuation. So this is why we call it connected, because it's the correlation function of the fluctuation. And you can do this in the following way. So you sum over all the pairs of particles. You make the product, if these are velocity, you make the scalar product of the fluctuations of particle I and j, right? So this scalar product is large if they point in the same direction and small otherwise. And you select only those particles whose distance between one each other is equal to r. Of course, this delta function will be some smooth delta function for real data, okay? But the idea is that you select all pairs at distance r, you measure what is their, the product of their fluctuation, but then you have to normalize. Normalize by what? By the total number of pairs at that distance, which is simply sum over I and j of r minus rij, okay? So the denominator here is the total number of pairs, okay? And you call this then your C of R, your connected correlation function. Well, there would be a lot to say here about this definition, which is not the standard one because we don't have phase averages. We can talk about that in my question and answer time on Thursday if you want. But for now, let's take this as a very sensible definition of connected correlation in your system. This is a spatial correlation, so equal time. So these two fluctuations are computed at the same time. So we're not making correlation at different times, but in different positional space at the same time, okay? So once you have computed the correlation, so first of all, why the correlation function is so important? Well, the idea is that by dealing with the fluctuation instead with the absolute behavior, you are taking away all the trivial part of collective behavior. That is all the part which is synchronized by some external factor or which is synchronized by the average behavior of the group. So this quantity, it's really the one able to detect self-organization, self-organized collective behavior in a system. So for example, if you had a system which is moving all together simply because there is an external field, the connected correlation function would be 0. On the other hand, if you have a system with no order parameter, but where interactions are strong and patterns emerge, you have a non-zero connected correlation function. So let me skip all this justification. Let's just take my words for this. This correlation function is really the best way, is the true hallmark of collective behavior. So because I'm very tight on time, executive decision, we say that there is collective behavior when there is non-trivial correlation function. So what non-trivial means? So what do we expect as the behavior of the C of R, the connected correlation function as a function of distance? Well, we have a decay of the correlation function with space. Why is that? Well, this is basically the average of delta Vi, delta Vj. When the distance between I and j tends to infinity, this will go to delta Vi times delta Vj averages, and this is going to be 0 because by definition, the average of one fluctuation is equal to 0. So this correlation function, if it is correctly defined and measured, must go to 0. And so you can always define a range, a spatial range of this correlation, right? So define a length scale, which is a crucial player in what follows. So psi, the range over which the correlation function decays, is the correlation length. Well, basically, we'll want to compute how the correlational length depends on the system in theoretical models. Okay, so on rather general grounds, then you can say that the correlation function has a short-range part that you can think about as an exponential. It doesn't need to be an exponential, but an exponential is good enough to fix ideas. And then you may have a long-range part, a power law 1 over r to some exponent alpha. Okay. So this is, say, the behavior for distance much larger than some microscopic landscape, okay? So you have a short-range part, which is ruled by the correlation length, and a long-range part, which is what remains when the correlation length is very large. So what do we expect from Xi? What are the typical behavior we have from Xi? Well, the easiest case, so case number 1, is then when Xi is larger, but of the same order of the microscopic length scale. So A is the microscopic length scale. So for example, the interparticle distance, the distance between the nearest neighbors in your system, some microscopic length scale. So this is typically always true. So the correlation length could be largish than the microscopic length scale because the interaction is typically in all these systems short range. But if nothing particularly happens, you have that the Xi is not much larger than the microscopic length scale. Okay, so when this is the case, you say that there is, let's say, nothing special going on, okay, in the system. However, you may have cases in which Xi, the correlation function, extends much beyond the microscopic details, the microscopic length scale of the system. So this is, I would say, quite special. So normally it doesn't happen if there is nothing particular in the system, nothing special. So this is what we define as having strong correlations. Okay. And this is, in my opinion, your best definition of having collective behavior. So you have collective behavior when you have non-trivial correlation, meaning when the range of your correlation of the spatial correlation function extend way beyond the microscopic details. And this is also the case in which you can start doing statistical mechanics and statistical physics. In other words, is the case in which you can at least hope that the macroscopic details of the system do not matter enormously, right? If the correlation length is of the same order as the interparticle distance, probably you're not in that case. But then there is a third case, which is very special, which is when the correlation length is infinite, okay? So in this case, if this happens, then your C, which is e to the minus r over xi over some power law, if xi is infinite, you simply remain with the power law. So in this case, you say that you have scale-free correlations. Scale-free because the only scale of the correlation is the correlation length. The correlation length has been blown to infinity, and then you have no scale. Or you can also say that you have long range, in this case, long range correlation. Now, of course, in a real finite size system, so if you are at finite size, and if you are doing experiments on biological system, you're always at finite size, then you can never measure a bona fide length scale which is infinite. So if the bulk correlation length is infinite, what you observe in finite size, that you observe that the actual correlation length psi scales like the size L of the system. So when you observe that Xi scales with L, so that larger systems have larger correlation length, then you are in the scale-free case, okay? So this is a very special case. Normally, there must be reason for Xi to be infinity. For example, most of you know one, and this is what happens when you are at the critical point. However, we have to be careful because there may be other explanations why the correlation length of a system is infinity. So basically, my whole lecture will be about this because what we find in flocks. So what do we find in real flocks of birds? So we have data in flocks of birds. We went out, we measured the position and the velocity of all the birds. And what we found is that the correlation length the correlation length defined exactly as I told you before of the velocity correlation functions, right? So C of V as a function of L scales linearly very well with the size of the flock. So we measured flocks of several sizes, several size L, which are in the range between, I'd say 25 meters and 200 meters. We measure the correlation function in all of these flocks, and what we find is that the velocity correlation function scales with the size of the system. So you have a scale-free correlation. What is interesting is that not only the correlation length of the velocity fluctuation is scale-free. So remember, the velocity fluctuations are defined in this way, are the VI minus 1 over n sum over k of vk. So they are vectorial quantities. But what you can do is that you can also measure the speed fluctuations. So these are animal flying about 10 meters per second, but they do have fluctuations. So sometimes it's 9, 8, 11, 12. So they have fluctuation in the speed. So what you can do is that you can define, of course, the modulus of the vectorial VI. So this is what we call the speed. So the speed is just the modulus of your degrees of freedom. And then you can measure the fluctuation in the speed. So VI, but now is a scalar, minus the average speed of the flock, okay? Sorry, this is the average speed of the birds in the flock. And you compute the correlation function exactly in the same way. And so you can compute also the correlation length exactly in the same way. Well, what you find is that even the speed correlation length scales linearly with the size of the flock. So scale free also for the speed fluctuation. So this is the experimental result we want to explain. The fact that you have, so in flocks, in real flocks, correlations of the velocity and speed fluctuations are scale-free. So the point I will try to develop in the next lecture is how relevant is this? Well, this by me, I mean how biologically relevant is this? So this certainly seems some relevant piece of phenomenology, because having a scale-free correlation really gives flesh to the qualitative catchphrase that the whole is more than the sum of its parts, right? So this is a sentence you always hear in collective behavior. The whole is more than the sum of its parts. But what does it mean? Well, this would be a rather sharp definition. So if you take a scale-free system and you divide it in two pieces, well, you have something which is qualitatively different because you have killed this system spanning correlation in the system. However, the important point we want to understand is this very specific and peculiar scale-free phenomenology. Is it due to biology or is it just due to physics? So is that an adaptive feature of the system? Is something that was achieved by adaptation and evolution by tuning some biological parameter? Or is it something that's just automatically given to you by physics and math? And this is certainly a relevant question, because if you don't ask this question first, you risk ending up giving explanations, biological explanation, which are completely uncalled for, right? So this is what we want to understand. Is this scale-free phenomenology due to physics, or there is something more? And then it must be due to biology, and we need to find the biological mechanism granting scale-free correlation. So to answer this question, what we have to do is that we must do theory. So let's start doing some theory. Again, I will skip all the introduction. So let me say that the most important ingredient over which all theoretical models of collective behavior, well, most of the collective behavior models are built, is the concept of imitation. So the idea of the first people building collective behavior models was each animal is imitating the behavioral state of its neighbors. And in the case of self-propelled system, each animal is just imitating the motion state of its neighbors. This was the idea not only of Vicek at the beginning, but also of biologists before Vicek, people like Okubo and co-workers. So the idea is, let's try to write a models which is just encoding the mechanism of local imitation, okay? And of course, because we, well, at least some of us are physicists, the imitation is clearly connected to the concept of ferromagnetic interaction. So we will end up writing models more or less for what we can call the flying ferromagnets, because imitation is just a ferromagnetic interaction. So let's start by putting down some Hamiltonian. Well, why Hamiltonian? Well, you can call it Hamiltonian, you can call it cost function, but let's say it's generally speaking what the system will try to minimize if not for the noise, okay? So the most basic imitative interaction that we can write for the velocities in the system is something like that. You put sum over I and j up to n of vi minus vj square times nij. So what is this? So nij is the interaction matrix or adjacency matrix, right? So it's something which is 1 if I and j interact, and 0 if they don't interact. So there are many ways to choose this matrix, but for the moment, let's say that the only important thing you have to remember is that this is something which is short range. There's topological, metric interaction, many details here, and I guess Julien Tailleur will speak about that, but for the moment, this is just some good old short range interaction. So you only interact with your nearest neighbor, let's say, okay? So nearest neighbor interaction is good enough. So this part here is just ensuring that this is the imitation. It's imitation because clearly it's minimal when the velocities are all the same, okay? So at the beginning, people, to simplify things, were also assuming that the modulus of the velocities were constant and equal to all of them. So there was a fixed speed constraint that we will relax in a minute, but the original models had a fixed speed. So once you have this cost function, then you can write some dynamics, okay? So, and the easiest dynamics that you can write is a Langevin kind of dynamics in which you say now that the derivative of Vi with respect to t, it's equal to what? Well, some force derived by that Hamiltonian, okay? So this is what we could call force, but in quotes, of course. It's not a real Hamiltonian force, okay, because that is the derivative with respect to the velocity, but it's something we tend, try to have Vi as close as possible to the velocity of its neighbors, okay? And then we put some noise, they call Zi, okay? So this is just some white noise. So the correlator of Zi times t prime, let's say is delta ij, delta t minus t prime times some amplitude gamma, right? So this is just some white noise. But the important point is that we have also a second equation, which is dx over dt, of course, equal Vi. So the equation reminding us that the Vi's are actually velocities. So the first equation is really the ferromagnetic part or the imitation part of the equation, while the second one is the self-propulsion. So without the second equation, this would be just a time equation for a normal standard equilibrium ferromagnet. But now we have that the positions of these small arrows are actually moving following the arrows, right? Because this is a self-propelled system. So this kind of model is what we call, let's say, Vicek class. Sorry, Dicek class, because this was introduced by Wiksek and co-workers in 1995. There are many variations of these models, but the idea is this one. There is local alignment plus self-propulsion. So this is why we can call this a kind of a flying ferromagnet system. Okay, so many things happen in this system. For us, the only important thing we should remember is that at low enough noise, so if noise is low enough, you get collective order. So the mechanism of local imitation, then, if the noise is low enough, grants you the collective motion of the system. So this system form flocks, meaning system which have a large order parameter that go around all at the same time, okay? The second point you should note of this system is that this system is out of equilibrium. So it's not an equilibrium behavior. Why? Because the Nij, the interaction network, depends on time through the second equation. For example, if you say that Nij is a nearest neighbor interaction matrix, but then who is neighbor of whom depends, of course, on the position, but the position depends on the velocities, and the velocities depend on Nij. So there is a feedback, of course, between the position and the velocities, which makes Nij depends on time. And so this is why H, this function H here, which includes the interaction matrix, is not at all a standard equilibrium Hamiltonian, right? Because Nij in principle depends on T. Okay, so these are the only two things I would like you to bring home about this Wiksek class collective behavior model. And I'm sure that Julien Tailleur will talk more about this. Oh God, it's already 10. Okay, so as I said at the beginning, this was introduced with fixed speed. So the imitation dynamics was only imitation of the mutual orientation, so of the direction of motion. However, we want to say something about the speed fluctuation, and so we have to introduce some mechanism of speed control. Okay, so if our Hamiltonian is this one, sum over I and j vi minus vj square nij, we could say that now we can leave the modulus of vi free to fluctuate, but if we just put this Hamiltonian, okay, they will imitate also their the speed of their neighbors. Okay, so not only their orientation. So this imitation part will grant that they will try to have also the speed equal to the one of their neighbors. However, speed is not a cyclic variable like orientation. So if we don't put any other piece in this cost function, well, then speed will just be not bounded. It will be free to be as large or as small as you want. So it cannot be even with fluctuation, but they have a cruising speed which is close to some biological value, right? So even though Vi is free, it should still be close to some biological value, V naught. So we cannot just leave the speed free to drift, to get any value, right? So what we put is an extra piece, which we call sum over I V of Vi, and this is the speed control potential. So something which keeps the speed of each animal around some natural value, okay? So what is the simplest form of this VI? Again, let me cut a lot of details. So first of all, VI must be rotationally invariant. So let's say it must depend also on VI square. Why is that? Well, we don't want to break by hand the rotational symmetry of the system by putting a speed control potential. We do not want to dictate to birds in which direction to fly by putting a speed control potential, right? So also the second point is that this must confine the speed around some natural value V naught. So we will have to have some form like VI square minus V naught square to the power P. So this is the easiest way to confine vi square around some natural biological value. So remember, v naught is the biological reference value. So for example, for starlings is 10 meters per second, okay? And finally, p must be even. And I leave you understand must be, well, otherwise, if it's not even, you will not have a minimum at v naught, right? So must be even, so v has a minimum at v naught, right? So we only want to consider these three very simple and basic conditions, right? So rotational invariant, confining around some value, and it must have a minimum there, right? So the simplest case then we can imagine is P equal 2, right? So a speed confining potential of this sort, vi square minus v naught square. And let's put some constant in front of this, g, right? For dimensional reasons, because then our Hamiltonian, so our cost function becomes sum over I and j, vi minus vj square. So this is the imitative part, plus g sum over I, vi square minus v naught square. Okay, so imitation and speed control. So what is the shape of this speed controlling mechanism, of this speed controlling potential? Well, it's very sensible. It's something like that. So if this is the modulus of VI, right? So here you will have V naught, your reference biological cruising speed. So this potential is something like that. It has a minimum at V naught. And depending on the value of G, you can have a sharper minimum, so something which has a higher curvature, right? Or it can be a very shallow minimum, okay? So this is a large G, and this is a small g. We'll come to the value of G in our final lecture. That will be very important. But for the moment, this is just a very reasonable potential with a minimum around V naught, keeping your speed around the reference value. Okay, the last step we have to do at this microscopic level is something which is quite bold, but I need it for the following, and is the following, is the quasi-equilibrium hypothesis. So quasi-equilibrium flux. So the Vixek class model that I've described up to now, so imitation plus speed control, is really a great model for a large variety of systems. So not only flocks of birds, school of fish, but also disordered systems like swarms of insects, bacterial cluster, and so on. But now I want really to go to flocks, right? We will be describing flocks, and in flocks, the order parameter is very close to 1. Actually, in flocks, the order parameter, I give you the real numbers, is something between 0.9 and 0.95. So it's quite large. So meaning that these are really highly ordered systems. So remember that phi is 1 over n sum over I of vi over the modulus of vi modulus, okay? So in this strongly ordered phase, the important thing to do, to understand, is that the reshuffling of the network is slow. So when phi is close to 1, Nij, so the interaction network Nij of t is slow, okay, has a slow reshuffling. Now, why is that? Well, clearly, the reshuffling of the network, right, depends on the velocities, right? So because, for example, two particles I and j that are interacting at some instant of time because they're close to each other, but then if their velocities are divergent at the next instant of time, they will be far and not interacting anymore. So certainly depends on the velocities, but it's more important to understand that it depends on the fluctuations of the velocities. If all the birds are going very fast, but all exactly in the same direction, then if you go in the center of mass of the system, you will have no mutual motion of the particle with respect to each other. So the order parameter really is directly connected to the relaxation time of the interaction network. And indeed, you can measure that. So what you can do is to measure the time correlation function of the network, which is something like that. You take sum over I and j, nij at times t naught, nij at times t naught plus t, right? And you average this over t naught. So this is now a time correlation function. So in this, you can plot how this correlation function decays with time, and you can then select the scale. And this is the scale of decorrelation of the network. So let's say it's the scale over which you change your neighbors, right? So this tau network is in real flux about 5 seconds. So to fix ideas, let's say that you can say that you take 5 seconds to change half of your neighbors, right? So this seems really slow. However, slow with respect to what? Well, what you can also measure then is the correlation function of the degrees of freedom you're measuring. So the time correlation function of the velocities. So you can measure delta vi at time t naught, delta vi, vi at time t naught plus t, right? Average over t naught. So this is now another correlation function in time, which is measuring how quickly the degrees of freedom are decorrelating with each other, right? So this will give you another time scale. Let's call relaxation time scale of the degrees of freedom. You can measure that. And what you find is that this is of order 0.1 second. So the conclusion here is that the interaction reshuffling time, tau network, is much larger than the relaxation time of the velocities. But again, this is true in flux, actually in flux of starlings, not in every biological systems, not at all, right? For example, this is not true in swarms of insects, right? But in flux, this is true. So because we are interested now in building a statistical mechanics for the relaxation of the velocities and of the speed, okay? What we will do is that because of this phenomenology, so we make an assumption, and the assumption is that Nij does not depend on time. So this is also called fixed network approximation. So before you jump on your chair and leave, okay, let me tell you that this has been now, at least in flocks of birds, tested quite carefully, and it works. So I'm not saying that flocks are at equilibrium. Depends on the time scale over which you're studying the systems. So if you're studying the system of a time scale of 0.1 seconds, well, then yes, the system is effectively at equilibrium. If you're studying another thing, for example, self-diffusion in the center of mass and so on, then the system is certainly out of equilibrium because you do have diffusion. But for what follows, we want to introduce statistical mechanics models, a simple statistical mechanics model for these things. And then we can assume that the system is at quasi-equilibrium, so that the network is fixed. So if you do this, then your Hamiltonian has now, is actually becoming some kind of real Hamiltonian, because Nij is now fixed, is a nearest neighbor short-range interaction matrix. So you have your imitative part, we have our speed control part, okay? And then you have the dynamics, which is some standard now Langevin dynamics of this kind plus noise. And now we don't have the other equation. So we kill the other equation, the dx over di equal vi, okay? We kill it. Momentarily, we kill it, okay? Because we're assuming that you are at quasi-equilibrium. Now, once we do this assumption of a fixed network, it really doesn't make much sense to go on calling our degrees of freedom VI, because they are not velocities anymore, right? They are only morally velocities. So in the following, I will replace VI with another letter phi I. In this way, we will remember that everything we're doing is under the umbrella of the fixed network approximation. Okay, even though we can do simulations of the system even without a fixed network approximation and see how good is that. Okay, so okay, so what we need to do now in only 15 minutes is to go from a microscopic kind of model where you have the individual particles, so you have this index I, to a field theoretical model where you have continuous fields. So what we need to do is to do a coarse graining to field theory. So coarse graining means replacing, going from a set of microscopic variable phi of t, which originally were our velocity, to a field phi of x and t. And coarse graining essentially means doing local averages, right? So you have a bunch of particles in a small volume V, and you replace that with some local average. So local average. So you don't need to know more about coarse graining than this. So we are doing some local average so we can have continuous fields. So there are various ways to do that. You can actually do some coarse graining and try to really see what happens to your original microscopic model through coarse graining. Or you can take a more phenomenological Landau-Ginzburg approach. And this is what I will do, is say, okay, correlations are long range, so hopefully microscopic details would not matter much. So even the details of how I actually do this coarse graining will not be very important. So we do the coarse graining in a very practical and phenomenological way. So let's go back to our original microscopic Hamiltonian, and let's see how this transforms. Well, what becomes of this under coarse graining? So imitation plus speed control, that now is no longer speed, is the modulus of my degrees of freedom. Okay, so first the imitation part. Sorry, I'm going to be really pedestrian on this part. Okay, so how the imitation part changes. So sum over I and j, nij, pi minus pj squared. Okay, so what the first thing we can do, so remember this nij is just a short range, so a nearest neighbor interaction. Doesn't need to be a regular lattice. It could be a Poissonian distribution of points in space. Actually, birds are very much Poisson distributed in space, which means randomly distributed in space. If you try to look for some structural order in the position of birds in a flock, you find nothing. They're as good as a gas, more or less. So you have a random distribution in space. Okay, so this nij is just a short range nearest neighbor interaction matrix. Okay, so what we could do, first of all, is to divide and multiply by the nearest neighbor distance square. So let's say that A is the nearest neighbor distance, okay? And then we also multiply and divide by the same factor A, nearest neighbor distance, to the D. So A is the nearest neighbor distance. So it's the scale of the direct interaction between the birds. Why we're doing that? Well, clearly, because now you see that here, what you have is, let's say, an imitation of a gradient, right? So you have phi minus pj over a square, right? So we say that this, let's say, not is equal, but goes to, morally goes to, under coarse graining, what? An integral. So the sum becomes an integral over d dx of the gradient of phi square, okay? And you also have that extra factors out, a to the 2 minus d. So this a to the d became the integration Jacobian ddx, right? These two factors goes out in this a to the 2 minus d. And this actually means, so this is the gradient of a vector. So this means dA phi b, dA phi b. Okay, this is what this means. Right, so this is the good old gradient square of field theory interaction. This is the most obvious way to reproduce imitative interaction. So the gradients in the cost function, in the Hamiltonian, prevents your field to have big local changes, okay? And so it pushes the field toward having a smooth behavior, which is the same as having an imitative behavior at the macroscopic level. Okay, so this was imitation. What about the speed control part, the modulus control? Okay, so in speed control, the term was G sum over I of phi I square phi naught square. Okay, we can be very pedestrians and say that this sum simply go to an integral. So G integral over the dx of phi x square minus phi naught square. So this is a square, and here there was also a missing square. Okay, and we have an extra factor a to the minus d to compensate for this integration. Now this, I apologize, is very pedestrian, and it is important that you understand that this coarse graining only holds when you are in the ordered phase, which is okay for flux. I had 2 pages to do explanation in this, but so you're doing a coarse graining. Coarse graining means that you're doing an average of the local velocities of your particles. So if you are in the ordered phase, yes, the coarse grain field will also have a value, a modulus that will be close to phi naught. On the other hand, if you have a disordered system like a swarm, even though each particle has an average velocity v naught, when you coarse grain, you get a zero field, phi equal to 0. So it is important that this coarse graining, these microscopic terms only goes to these very similar coarse grain terms only in the ordered phase at low noise and low temperature. Otherwise, you have something different. Okay, but anyway, if we collect our pedestrian parts, what we get is, for the new coarse graining Hamiltonian, is something like that: an integral over the dx of a to the 2 minus d gradient square of phi plus a to the minus d g of phi square of x minus phi naught square square. And if we develop now this square, so we have integral over the dx a to the 2 minus d gradient of phi square. So we have plus a to the minus d g phi to the 4th minus, a very important minus, 2a to the minus d g phi naught square and phi square of x plus irrelevant constants. Okay, so we don't count a constant here. Now we recognize that we can rescale the field. So rescale the field phi of x. Why? Because we want to absorb this term here, this prefactor here, because it's handier for the next of the lectures to have a factor 1 in front of the gradient. Okay, so we can rescale the fields. So we end up with an Hamiltonian, which is very well known to most of you, which is the following. Let's say we put a factor 1/2 in front of the field, which is now rescaled, plus 1/2 mu square phi square of x plus lambda phi 4th of x. So some comments here. So you remember that in front of the quadratic part here you had a minus. Okay, now I put a plus and a factor which I call mu square. So this mu square, okay, for us is negative. It's called mu square because this is what is called the mass. Well, the mass square in field theory. It's a relic from the particle physics field theoretical part, but it's nomenclature I really cannot avoid to use, right? But never mind, mu square will be negative because we are in flux, and flux are ordered. And because they're ordered, here you have this minus. This minus, remember, comes from the speed control part, right? From this minus here, okay? So mu square for us will be negative, okay? You have the quartic part. So this lambda is what we call the coupling constant. Okay. And well, so we ended up with something which is very well known, which is called the Landau-Ginzburg theory. Landau-Ginzburg, or also called lambda phi 4, or because this is a vectorial case, is also called ON model, where n is the number of components of the field. Okay. Now, okay, in this Landau-Ginzburg Hamiltonian, it's important again to remember that, so in this potential, it's called V phi, which is 1/2 mu square phi square x plus lambda phi 4 x, okay? So this potential as a function of phi is something like that, right? Okay, remember this was pinning the modulus of the field around V naught. So the important point for us is that this mu square is negative. Remember this. Okay, but if we want to plot this potential now, not as a function of the modulus, but as a function of the whole degrees of vectorial degrees of freedom, what do we have? Well, we have something like that. Okay, so this is V, and I'm drawing it in the case of a two-dimensional field. So this is phi x and phi y, but of course the field could be three-dimensional. In the case of flux, it's three-dimensional, but I cannot draw it in three-dimensional, but it's the same thing. So this is the part mu square phi square, which is negative. And this is the steep increase like lambda phi 4, okay? So this is what is also sometimes called the Mexican Hart potential, and it will be the kind of field theoretical potential we working on. The important point you have to see here is that this potential has got a line of minima, a continuous line of minima, right? So the bottom of the potential, and this continuous line of minima will be really a game changer for in the next lecture. The fact that you have this continuous line of minima, that you will have a continuous symmetry breaking, will give us a lot of important phenomenology connected to what we find also in flux. Okay, it's about 10:30. I think I can stop here. I cannot compress any more material in 2 minutes. So the next time, what we will do is to try to use this very standard and simple field theoretical model to try and understand whether the long-range correlation, the scale-free correlation that we find in flux are due to some general physical mechanism, or to there is something more that we need to explain at the biological level. Okay, Julia, I think I will stop here.
Thank you. All right, so I asked if there are some questions, and then, well, I think it's an effective way to ask questions will be during the question and answer, but if there are some questions now, ask and I will repeat to Andrea. No? No questions. So
okay,
actually the broadcast was okay, so we could hear you well.
Okay, good.
So well, see you tomorrow. Hopefully okay. With without any problem. So at 8, so you are in the morning again, I think.
Yeah. Okay.
So indeed. Okay.
Okay, and thank you to the next speaker for the half an hour. Bye bye, guys. See you tomorrow.
Thank you. Bye. Yeah.